The universe, when seen from Earth, appears to be filled with matter. The points of light you see in the night sky seem to suggest a crowded cosmos. But in reality, the story is completely different. Because when you measure it precisely, that picture is almost entirely reversed. The latest data from NASA, combined with deep field observations from the James Webb Space Telescope, shows that everything humanity has ever seen accounts for less than 5% of the universe. The rest is not made of stars, not galaxies, and not anything you can observe with any telescope. The remaining 95% is almost entirely invisible. And what makes this even more striking is that this unseen part is what actually governs how the universe behaves. Tonight, we're going to explore the structure of that absence. We'll move through regions of space stretching millions of light years, where matter is almost completely absent, and examine what is really happening when space itself begins to pull everything apart. As always, I'd love to know where in the world you're listening from and what time it is where you are. And don't forget to subscribe to Space Lol so you don't miss the latest videos. Let's begin with something familiar: the night sky. You look up and see thousands of points of light. The first impression is natural. The universe appears crowded, as if something exists in every direction. But that impression does not reflect reality. In our Milky Way, there are about 200 to 400 billion stars, an enormous number. But even under the most ideal conditions, the human eye can only see around 2,500 to 5,000 stars. That means you are seeing less than 1/1,000,000th of the galaxy. If the Milky Way were an ocean, what you see would be just a few drops of water. Most of those stars are also relatively close to us, only a few thousand light years away. While the entire galaxy spans about 100,000 light years, you are observing the universe through a very narrow window of perception. Thanks to the Gaia mission, by 2026 we have mapped more than 1.8 billion stars, a very large number, but still only a small fraction of the hundreds of billions that exist. Even with the most advanced technology, we have not yet observed most of our galaxy. And when you place these stars into three-dimensional space, one thing becomes clear: they are not close to one another. Try to imagine this. If the Sun were the size of a grain of sand, the nearest star would be about 30 kilometers away. Between those two grains, there is nothing significant. No planets, no dense matter, only a few scattered atoms. Light takes more than 4 years to cross that distance, and that is the closest case. In many other regions, the distances are even greater. This leads to a very simple conclusion. Most of the space in the galaxy is empty. So if the universe contains so many stars, why is the night sky dark? This is known as Olber's paradox. The answer lies in 3 things. The universe has an age light takes time to travel. Space is expanding. The darkness you see is not the absence of light. It is a sign of a universe that is changing. We live on a small island of light, in an ocean that is almost entirely empty. What you see is not the whole picture. It is only a very small slice of reality, and if you think that is already empty, then what comes next is even more surprising. Because this emptiness does not only exist between the stars, it exists within matter itself. If the previous chapter showed that the universe appears empty when seen with the eyes, then in this chapter we measure it with numbers. The question is, how full is the universe really? Modern observations show that if you take all the matter in the observable universe and spread it evenly across all of space, the average density is only about 6 hydrogen atoms per cubic meter, not 6 million, not 6,000, just 6. In the room you are sitting in right now, each cubic meter contains tens of trillions upon trillions of molecules, a number so large it is almost impossible to fully grasp. Out there, in deep space, the same volume contains only a few particles of matter. The difference is almost impossible to imagine. That means you could travel millions of kilometers through space without encountering anything significant. No surface, no obstacle, only emptiness. The universe is not built from things that exist, but from the distances between them. But what is even more surprising is this. This emptiness does not only exist on large scales, it exists within matter itself. Look at an atom. If you were to enlarge it to the size of a stadium, the nucleus would be no bigger than a pea at the center. The electrons would be extremely far away, at the outer edges of the stands. And between them, almost nothing. More than 99.9999999% of an atom's volume is empty space. That means the chair you are sitting on, your hand, your body are, in essence, almost entirely empty. So why do things still feel solid? The answer is the electromagnetic force. Electrons repel each other, creating the sensation of contact. You are not truly touching matter. You are being stopped by invisible force fields. If all the empty space inside atoms were removed, all of humanity could be compressed into a volume smaller than a sugar cube. This is not a hypothesis. It is a direct consequence of atomic physics. This leads to an important conclusion. Even matter itself does not truly fill space. At the cosmic scale, empty space between galaxies. At the atomic scale, empty space within matter. Emptiness is not the exception. It is the rule. But at this point, a larger question begins to emerge. If the universe is empty at every scale, then why is it this way? And more importantly, the matter we've been discussing accounts for less than 5% of the universe. What is the remaining 95%? Not atoms, not electrons. Yet it is what determines how the universe behaves. And that is where the real answer begins. When we realize that 99.9% of an atom is empty space, and that the density of the universe is so low that only a few atoms exist per cubic meter, an inevitable question emerges. Why hasn't everything fallen apart? Why does our Milky Way, with hundreds of billions of stars orbiting a central point, not simply disperse into space? According to the laws of physics as we understand them, that should not be possible. That means galaxies are being held together by something we cannot see. This story begins with a contradiction in astronomical data. In the 1970s, astronomer Vera Rubin observed spiral galaxies and noticed something unusual. According to Newton's law of gravity, stars located at the outer edges of a galaxy, being farther from the center, should orbit much more slowly than those closer to the core, much like how planets farther from the sun move more slowly than those closer in. But in reality, the opposite was observed. Stars at the outer edges of galaxies move at nearly the same speed as those near the center. At those speeds, the gravitational pull from visible matter is not enough to hold them in place. They should have been flung outward billions of years ago. This led scientists to a clear conclusion. There must be something else there. Something with enormous mass that creates gravity but remains completely invisible. It does not emit light. It does not reflect light, and light passes through it without being affected. Scientists call it dark matter. By 2026, measurements from the Euclid Space Telescope and the James Webb Space Telescope have reinforced the conclusion that dark matter is not just a hypothesis. It is a fundamental component of the universe. Dark matter surrounds every galaxy like a massive halo, known as a dark matter halo. If the Milky Way spans about 100,000 light-years, its halo may extend beyond 1 million light-years. Most of the galaxy's mass lies outside what we can observe. You can imagine a galaxy like a swirling vortex. The stars you see are like glowing particles of dust in motion. But what actually holds that structure together is an invisible mass surrounding it. We do not infer the existence of dark matter only from the motion of stars. We also observe its effects through a phenomenon known as gravitational lensing. When light from a distant galaxy passes through a region with a large amount of mass, space itself becomes curved, and light follows that curvature. This creates stretched images, arcs of light, and distortions that cannot be explained by visible matter alone. We do not see dark matter, but we see its effects everywhere. But what is dark matter really? This remains one of the biggest unanswered questions in modern physics. To find the answer, scientists have built some of the most advanced experiments ever created. One of them is located deep underground in South Dakota, in the United States. It is called the Lux-Zeppelin experiment. In a mine more than a mile underground, scientists have placed a massive tank filled with ultra-pure liquid xenon. Surrounding it are multiple layers of shielding to block all external radiation. They are searching for something extremely subtle, a rare collision between a dark matter particle and an atom. If such an event occurs, it would produce a very faint flash of light. So far, no definitive signal has been detected. Dark matter remains completely silent, but that does not mean it is not there. If it exists, then it is passing through you right now. Billions of particles could be moving through the Earth, through your body, without leaving any trace. This leads to an important realization. What we call empty space is not truly empty. It contains an invisible structure, a kind of cosmic scaffolding that allows matter to exist. Without dark matter, the first hydrogen atoms in the early universe would never have gathered enough to form stars. Without stars, there would be no light, and no structures as we know them. Most of the structure in the universe is determined by things we cannot directly observe. However, no matter how important dark matter is, it is not the most dominant force. When we look farther out, beyond galaxies, and observe the vast regions between galaxy clusters, something else begins to emerge. Not a force pulling things together, but a force pushing them apart. If dark matter is the glue that holds the universe together, then something else is doing the opposite. A force that does not preserve structure, but gradually weakens it over time. And even dark matter is not what ultimately governs the universe. Behind it lies a component that makes up nearly 70% of the universe, something not only invisible, but directly tied to the expansion of space itself. And to truly understand the emptiness of the universe, we cannot stop at what holds things together. We must look at what is pulling everything apart. That is when the story moves to an entirely different level. When we look at vivid images of stars, it is easy to assume that matter is spread evenly across space, like sand across a desert. But on the largest scales, reality tells a very different story. The universe is not a uniform soup. It is an organized structure, a vast and intricate network so immense that any map humans have ever drawn becomes insignificant. Scientists call this the cosmic web. That means matter is not everywhere. It is concentrated along very specific paths. Imagine looking at a gigantic spiderweb covered in morning dew, suspended in complete darkness, stretching into a space with no end. Thin, glowing threads connect dense nodes, leaving enormous empty regions in between. Our universe operates in a similar way. Matter does not gather randomly. It is shaped by structures that formed very early, primarily guided by dark matter. Most of the space between these threads is almost completely empty. This web consists of 4 fundamental components that define the large-scale structure of reality. First are the cosmic filaments. These are structures stretching across hundreds of millions of light years, formed primarily from dark matter, but strong enough to guide the flow of hydrogen gas and galaxies. Next are the nodes, where filaments intersect. These are the densest regions, where galaxy clusters and superclusters form. The third component is the sheets, thinner, extended structures that resemble vast walls of matter. And finally, occupying most of the volume, are the empty regions between these structures. By 2026, thanks to observations from the James Webb Space Telescope and large-scale survey data, we are able to see clearer evidence of this web than ever before. Observations show that even in the very early universe, just a few 100 million years after the Big Bang, these filament-like structures had already begun to form. This suggests that the web is not a random outcome, but a natural consequence of how matter distributes itself under gravity. The scale of this structure goes far beyond ordinary comprehension. If each galaxy, like the Milky Way, is just a small point, then a single filament can stretch across hundreds of millions of light years. These filaments act as pathways for matter, guiding gas and dust as they move and accumulate into denser regions. What you see within galaxies is only a small portion located along these structures. Some studies suggest that the geometry of the cosmic web shares similarities with other natural systems, such as neural networks in the human brain or biological networks underground. However, this similarity is mainly structural, reflecting how complex systems organize and optimize connections. When we map the universe in 3 dimensions, one thing becomes increasingly clear. Matter does not occupy most of space. It exists only along thin structures, like illuminated roads in a city at night, while most of the surrounding area remains in darkness. What you see is only the outline of a much larger structure. The universe is a network, but an extremely sparse one. Galaxies are not everywhere. They appear only along these thin filaments. If you leave a cosmic filament, the chance of encountering another astronomical object becomes almost zero. And this is the key point. The bright structures we observe, galaxies, galaxy clusters, are not the dominant part of the universe. They are only the visible part. What dominates lies in the space between them. Data from the Euclid Space Telescope is helping us build a more precise map of how matter and energy are distributed on large scales. Observations show that this network is not static. It is expanding. The filaments are thinning. The nodes are drifting farther apart. And the empty regions in between are growing larger. This suggests that another component of the universe is becoming more dominant than the web itself. Most of reality does not lie along the luminous threads, but in the regions where almost nothing exists. These regions are not random gaps. They occupy most of the universe's volume, and over time, they are becoming the dominant factor. And it is these empty regions that we must examine next. Because when we leave the cosmic filaments, we are not entering normal space. We are entering regions where the very concept of structure begins to disappear. When we study the cosmic web, most of our attention naturally focuses on the filaments and the dense nodes where galaxies gather. However, modern astronomical measurements up to 2026 reveal a very clear reality. Those structures are only the edges. Most of the universe's volume lies elsewhere. Scientists call these regions cosmic voids, vast empty spaces. That means most of the universe contains no significant structure at all. To understand the nature of the universe, we must accept a simple paradox. Emptiness is not the exception. It is the most common state. Matter, the things we can see, exists only along the boundaries of these empty regions. Cosmic voids are not small gaps between galaxies. They are enormous, irregular regions of space, with diameters ranging from 10 to over 100 megaparsecs, equivalent to about 30 million to more than 300 million light-years. Data from surveys such as SDSS and DESI show that more than 80% of the observable universe's volume lies within these voids. Within most of that volume, there is almost nothing to see. One of the clearest examples is the Boötes void, often referred to as the Great Void. With a diameter of about 330 million light-years, it is one of the largest empty structures ever observed. In a region of space of similar size under normal conditions, we would expect to find around 10,000 large galaxies. But in the Boötes void, only about 60 have been found. That means the matter density here is less than 1% of the average. Try to imagine that. If our Milky Way were located at the center of such a void, the night sky would appear almost completely empty. No distant spiral galaxies, no faint clusters at the cosmic horizon, only darkness stretching across hundreds of millions of light-years. Inside a void, what actually exists? The answer is very little. The density of matter drops to extreme levels, roughly one hydrogen atom per several cubic meters of space. This is the closest environment to nothing that physics allows. No dense gas, no significant heat from nearby stars, no strong magnetic fields. These are regions where physics operates in its most minimal state. But voids are not just empty. They have distinct physical properties. Measurements of the cosmic microwave background, CMB, show that these regions are colder than the rest of the universe. This is caused by an effect known as the integrated Sachs-Wolfe effect. In simple terms, when light enters a void, it is influenced by the gravitational field of surrounding matter. By the time it exits, space has expanded slightly. In other words, the light leaves the void with less energy than when it entered. This makes voids appear as cold spots in maps of the universe. The existence of supervoids such as Bootes or the Eridanus supervoid, which may span nearly 1 billion light-years, poses a challenge to standard cosmological models. According to gravitational theory, matter should be more evenly distributed, but reality shows the opposite. Over billions of years, matter has migrated. It has been pulled along cosmic filaments and concentrated into dense nodes. Meanwhile, the centers of voids have been gradually drained. The result? Voids become emptier and larger over time. Interestingly, some galaxies still exist inside voids. They are known as void galaxies. These galaxies live in near total isolation. No collisions, no mergers, no strong environmental interactions. This makes them natural laboratories. They contain more pristine hydrogen gas and are less affected by complex evolutionary processes. Studying them helps us understand how galaxies form under conditions close to the early universe. But the true importance of voids is not what exists inside them, it is what they are doing to the universe as a whole. Astronomers have realized that voids are not passive gaps, they act as regions of accelerated expansion. Data shows that voids are expanding faster than the average expansion rate of the universe. The reason is simple. In regions with a lot of matter, gravity can still hold structures together. But inside voids, there is almost nothing to resist the expansion of space. And those empty regions are expanding faster than anywhere else. This creates a chain reaction. As voids expand, they push matter farther away. As matter leaves, the void becomes emptier, and as it becomes emptier, it expands even faster. This is not a stable equilibrium, it is an accelerating process. On large scales, this means the structure of the universe is not just existing, it is being stretched. Filaments become thinner, galaxy clusters drift farther apart, and voids become increasingly dominant. This suggests that another component is driving this process. Not matter, not gravity, but something else, directly related to the nature of space itself. Up to this point, we have seen two sides of the universe. Matter, attempting to gather and form structure, and voids, where structure almost disappears. But one question remains unanswered. If matter creates attraction, what is causing space to expand faster? And if voids are expanding more rapidly, what is driving that acceleration? The answer does not lie in anything we can see. It lies in the fabric of space itself. And that is where we must turn to the next concept, a concept even more mysterious than dark matter, something that does not hold things together, but pulls everything apart. For decades, physicists believed that gravity was the ultimate ruler of the universe. According to that logic, because matter attracts, the expansion of the universe after the Big Bang should have slowed down over time, much like a ball thrown upwards slows down under Earth's gravity. But in 1998, a discovery completely overturned the foundations of modern physics. The universe was not slowing down. Instead, it was accelerating. That means the universe is not just expanding, it is expanding faster over time. The force behind this phenomenon is called dark energy. It is not matter, it is not radiation, and it does not resemble anything we are familiar with. Current models describe it as a form of negative pressure permeating the fabric of space itself. To detect the presence of this invisible component, astronomers used a special tool, Type 1a supernovae. These are explosions that occur when a white dwarf reaches the Chandrasekhar limit, about 1.4 times the mass of the Sun. The key point is this: these explosions occur under nearly identical conditions and produce nearly the same brightness. This allows scientists to use them as standard candles to measure distances across the universe. When observing very distant supernovae, two independent research teams discovered something unexpected. These supernovae appeared dimmer than expected. In astrophysics, dimmer is not just about light. It means they are farther away. This result led to a clear conclusion. The space between us and distant galaxies has expanded more than predicted. Some force is stretching the universe. By 2026, data from projects such as the Dark Energy Spectroscopic Instrument and the Nancy Grace Roman Space Telescope have provided more precise measurements. Dark energy accounts for about 68.3% of the total energy density of the universe. Most of reality is not matter, but something that pushes matter apart. If you combine everything we are familiar with, stars, planets, people, and even dark matter, they still make up less than 1/3 of the universe. The rest is something we cannot directly observe. This may sound abstract, but its consequences are very real. One of the biggest current mysteries is the so-called Hubble tension, a discrepancy in measuring the expansion rate of the universe. There are two main ways to measure it: observing the early universe through the cosmic microwave background, CMB, or measuring nearby objects such as Cepheid variables and supernovae. The result? They do not match. One method gives a value of about 67 kilometers per second per megaparsec. The other gives about 73. In simple terms, we are measuring the same universe, but getting two different answers. This difference is no longer considered a minor error. It is a real problem in modern physics. It suggests that dark energy may not be a constant. It may be changing over time, or possess properties we do not yet understand. So what is dark energy really? One of the most widely discussed ideas is that it is vacuum energy. According to quantum mechanics, empty space is not truly empty. It is a constantly fluctuating environment where virtual particles continuously appear and disappear. The important point is this: even nothing is not truly nothing. These fluctuations create a baseline level of energy in space, and perhaps that energy is the source of the repulsive force we observe. But the strangest aspect lies in how it behaves. If you have a container filled with gas and you double its volume, the density of the gas is reduced by half. But with dark energy, that does not happen. Its density does not change as space expands. This means, as the universe creates more space, the total amount of dark energy increases. The larger space becomes, the stronger this force grows. This creates a feedback loop. Expansion leads to more energy, which leads to faster expansion. And this process shows no sign of stopping. However, the strength of dark energy is not the same at all scales. At small scales, within your body, within the solar system, or within the Milky Way, gravity is still strong enough to hold things together. You are not being stretched. The Earth does not leave its orbit. But as distances grow larger, gravity weakens, and that is when dark energy becomes dominant. Imagine standing on a vast elastic sheet. Those standing close to you can still hold hands, but those farther away are being pulled apart at an increasing rate. And this is happening right now. Observational data in 2026 confirms a clear reality. Dark energy is dominating the universe. The cosmic filaments we discussed earlier are being stretched. Galaxy clusters are gradually becoming isolated. The distances between them are increasing over time. This does not destroy matter in a violent way. There are no explosions, no collisions. It does only one thing. It creates distance. Over time, that distance becomes so large that light can no longer cross it. Information can no longer travel. This leads to an important consequence. More and more regions of the universe become unobservable. They still exist, but no longer have any connection to us. If you look far enough into the future, galaxies beyond our local group will disappear from view, not because they are destroyed, but because the space between us has expanded too rapidly. This is how dark energy changes the universe, not by breaking structures apart, but by making those structures lose all connection with one another. Up to this point, we have clearly seen three major components of the universe: ordinary matter, which forms what we can see; dark matter, which holds structures together; dark energy, which pulls everything apart. But what matters more is how they interact. Matter tries to pull together, dark energy tries to push apart, and right now, dark energy is winning. This raises a deeper question. If this expansion continues, what will happen to the universe in the future? Will galaxies disappear completely? Will light no longer be able to travel between regions of space? Or are we moving toward a state where everything still exists, but nothing interacts anymore? To answer that, we need to go further. Not just looking at the present, but looking into the future of the universe. A future where emptiness is no longer just a feature, but becomes the final state. If the emptiness between stars already feels significant, the reality that astrophysicists are observing in 2026 goes even further. The universe is not only growing, it is changing the way information can exist within it. That means there are regions of the universe from which light will never reach us. The key concept needed to understand this process is the cosmic event horizon. Imagine you are standing on a ship in the middle of the ocean. There is a horizon surrounding you. Anything that crosses that line disappears from view. In the universe, this horizon is not created by the curvature of the Earth. It is defined by two factors: the speed of light and the expansion of space. As we saw in the previous chapter, dark energy is causing space to expand at an accelerating rate. At large enough distances, this expansion becomes so strong that the distance between 2 points increases faster than light can travel. This does not violate relativity, because no object is moving faster than light. It is space itself that is expanding. Imagine someone running on a moving walkway. If the walkway moves backward faster than the person can run, no matter how hard they try, they will never move forward. Light behaves in the same way. Photons leaving a distant galaxy today may never reach us, not because they lose strength, but because the space between us is expanding faster than they can cross. Most of the universe is already beyond our reach. Based on the latest observations from the James Webb Space Telescope and the Nancy Grace Roman Space Telescope, scientists estimate that about 97% of the galaxies in the observable universe are already permanently unreachable. This means that, even if we could travel at the speed of light, we still could not reach most of the universe. Those galaxies still exist. They still emit light, but their light will never reach us in the future. And this process is still ongoing. Each year, an estimated 60,000 galaxies cross the event horizon. This number is not just a calculation. It represents trillions of stars and countless planets gradually leaving the region we can interact with. If you look at deep field images from NASA, you see thousands of bright galaxies. But what matters is this: you are looking at their past. Many of those galaxies may already be beyond our reach today. We do not see them disappear, because their light takes time to arrive. But in physical terms, they have already left our interactable universe. This changes how we understand observation. When you look at the sky, you are not seeing the universe as it is. You are seeing what it used to be. And in many cases, what you are seeing no longer exists in the way you think. The observable universe is shrinking over time, not in size, but in information. This leads to an important consequence. Our access to information is gradually decreasing. Not because we are losing technology, but because the structure of space is changing. In the distant future, this expansion will continue. the number of galaxies we can observe will steadily decline. Within a few 100 billion years, all galaxies outside our local group will disappear from view. Our Milky Way and the Andromeda Galaxy will merge into a single large galaxy, and that will be all that remains in the sky. No distant galaxy clusters, no faint points at the cosmic horizon, only one structure, floating in darkness. This does not mean that other galaxies vanish. They still exist, but the distance between them and us has grown so large that light can no longer cross it. Expansion does not destroy matter, it destroys connection. And when connection is broken, information disappears with it. In that scenario, future observers will have no evidence of the Big Bang. They will not detect the cosmic microwave background. They will not see distant galaxies. From their perspective, the universe will appear as a small system, static and isolated. But that does not reflect reality. It reflects only what they can observe. The universe is not only expanding, it is hiding itself over time. As more space is created, the event horizon moves closer to us. That means more and more of the universe becomes inaccessible, not because it disappears, but because it moves beyond interaction. This is not a sudden process. It happens slowly, continuously, and irreversibly. We are living in a special phase where the universe is still visible on large scales, but that phase will not last forever. As distances continue to grow, another question begins to emerge. If galaxies are gradually separating from each other, if light becomes increasingly unable to cross the gaps, what happens to the possibility of communication between civilizations? Could there be other civilizations that we will never detect simply because the distance between us is too great? And that leads to another possibility, that the silence of the universe is not random. Perhaps the universe is not empty in a biological sense, but it is empty in terms of connection. And to understand that, we must go deeper into a question that has existed for more than half a century. A simple question that has never had a clear answer. If the universe is so vast, why have we not heard from anyone? For decades, humanity has pointed its largest telescopes and radio arrays toward the sky, listening for even the faintest signals from deep space, hoping to detect a sign of intelligence beyond Earth. Projects such as SETI have scanned millions of different frequencies, searching for structured patterns, something nature rarely produces. But so far, the result has been almost complete silence. According to the Drake equation, even within the Milky Way alone, there could be thousands, even millions of planets capable of developing intelligent life. If those estimates are correct, then the universe should be filled with signals. But reality is entirely different. No clear messages, no repeating artificial signals, no confirmed evidence of an extraterrestrial civilization. This question is known as the Fermi paradox. If the universe is so vast and so full of potential for life, then where is everybody? When faced with this question, people often consider extreme explanations. Perhaps civilizations destroy themselves. Perhaps there is a great filter preventing their development. Or perhaps intelligent life is extremely rare. But when we examine the actual structure of the universe, especially what we have seen in the previous chapters, another possibility begins to emerge. The problem may not be that no one exists, but that we cannot meet. First, consider the simplest factor, signal delay. Light and radio waves are the fastest things we know, but even they have limits. The Milky Way is about 100,000 light-years across. If a civilization on the opposite side of the galaxy sends a signal today, we would have to wait 100,000 years to receive it. To put that into perspective, 100,000 years ago, modern human civilization did not yet exist in its current form. That means two civilizations could exist and never know about each other, and this is only within a single galaxy. When we expand to intergalactic scales, the problem becomes far more severe. As we saw in the previous chapter, dark energy is causing space to expand at an increasing rate. This creates a physical limit. There are distances that light cannot cross, not because it is too slow, but because the space between 2 points is expanding too quickly. The distance is not just large, it is increasing over time. Imagine two civilizations in two different galaxies. They both send signals toward each other at the speed of light. But if the space between them expands faster than that speed, the signals will never arrive. No message is blocked. No signal is destroyed. They simply cannot cross the distance. In addition, the expansion of the universe produces another important effect: redshift. As space expands, the wavelength of light is stretched. This causes signals to lose energy over time. A clear radio signal, traveling across billions of light years, can be stretched to the point where it becomes indistinguishable from the background noise of the universe. This makes signals increasingly difficult to detect with distance. In other words, the universe does not need to silence civilizations. It only needs to ensure that their signals never reach where they are meant to go. This leads to an important consequence. The silence we observe may be a natural result of the structure of the universe. No catastrophe is required. No destruction is necessary. Only distance and time. Another key factor is the lifespan of a civilization. Even if intelligent life emerges, its duration may be very short compared to cosmic timescales. A civilization may last for thousands or millions of years, but if signals take hundreds of thousands of years to travel, it is entirely possible that, by the time a signal arrives, the sender no longer exists. This creates a kind of temporal mismatch. Civilizations must not only be close in space, but also overlap in time, and this is extremely rare. When we combine all of these factors, vast distances, the finite speed of light, the expansion of space, and short time windows, a clear picture begins to form. The universe may contain many civilizations, but they are isolated from one another. Not because they do not want to connect, but because they cannot. In this context, each galaxy is like its own island. On each island, there may be life, intelligence, and advanced civilizations. But between these islands lies an ocean that is nearly impossible to cross. And that makes this silence an inevitable outcome. This also changes how we think about loneliness. We are not necessarily alone because we are unique. We may be alone because the distances between us are too great. And those distances are not static. They are increasing continuously. But this silence is not the end. It is only part of a larger picture. Because when we look further into the future of the universe, another question begins to emerge. If distances continue to grow, if galaxies continue to separate, what happens when not only life, but matter itself becomes silent? Is the universe moving toward a state where everything still exists, but nothing interacts? To answer that, we must go even further, not just into space, but into the future of the universe itself. A future where this silence is no longer a paradox, but the natural state of everything. Every great story has an ending, and the story of the universe is no exception. But that ending does not arrive as a violent explosion or a sudden collapse. It comes slowly, quietly, almost imperceptibly. Scientists call this state heat death. As of 2026, cosmological models based on data about dark energy suggest that this is the most likely scenario for the far future of the universe. Heat death is not when the universe ends in the way we usually imagine. It is when all differences are erased. No region is hotter than another. No region can provide energy for a new process. In simple terms, energy spreads evenly across space and can no longer be concentrated again. And when that happens, nothing can happen anymore in the physical sense. The journey toward this state begins with something familiar: stars. Right now, we are living in the stelliferous era, an era where stars are still burning across the universe. But their fuel is not infinite. Hydrogen, the primary component of stars, is gradually being consumed. Within about 1 trillion years, the gas needed to form new stars will be exhausted. That means there will come a time when no new stars are born. Massive stars will die first. They explode as supernovae, leaving behind neutron stars or black holes. Stars like our Sun will become white dwarfs, hot remnants that slowly cool over time, and eventually, only red dwarf stars will remain. These stars burn so slowly that they can last for tens of trillions of years. But even they cannot last forever. One day, the final star will fade. At that point, the universe will no longer have any natural sources of light. The sky will become completely dark. What remains are only remnants. White dwarfs cool down, becoming black dwarfs. Neutron stars slow their rotation and gradually lose energy. Planets drift through cold darkness. On even longer timescales, some physical theories suggest that protons, the building blocks of atomic nuclei, are not perfectly stable. After an unimaginably long period of time, on the order of tens of decillions of years, far beyond trillions upon trillions, they may decay. That means even familiar matter does not last forever. Iron, rock, water, and even the human body will all break down into lighter particles. At this stage, the universe has almost no stable structure left. But there is still one thing that lasts longer than everything else: black holes. For a long time, they were thought to be eternal, but physicist Stephen Hawking showed otherwise. Through a quantum effect known as Hawking radiation, black holes can lose energy, extremely slowly, but not zero. A black hole with the mass of the Sun would take about 10 to the power of 67 years to completely evaporate. Supermassive black holes may last up to 10 to the power of 100 years. And when the final black hole disappears, no large structures remain. No galaxies, no galaxy clusters, no massive objects of any kind. Only elementary particles spread across an ever-expanding space. At this point, the universe reaches a state of maximum entropy. Entropy is a measure of how dispersed energy is. The second law of thermodynamics states that entropy always increases, and when it reaches its maximum, no differences remain. This is a state where nothing can change. No heat flow, no chemical reactions, no meaningful motion. In this state, time still exists mathematically, but it no longer has physical meaning, because no events occur to mark its passage. The universe becomes nearly uniform, cold, dark, and silent. Particles are so far apart that the chance of interaction becomes nearly zero, not because matter disappears, but because the distance between particles becomes too great. This is the most important point. The universe does not end through destruction. It ends through dispersion. Everything still exists, but nothing is connected anymore. No energy exchange, no transfer of information. From a physical perspective, this is the closest state to nothing that the universe can reach. In that context, a question is often raised: if all information is eventually dispersed, if no trace of history remains, does our existence have any meaning? This is not purely a philosophical question. It directly relates to how we understand time and our place in the universe. Modern research suggests that information may not be completely destroyed, but it becomes so dispersed that it can never be reconstructed. That means, in practice, all traces of structure become inaccessible. But that fact highlights something else. We are living in a very special phase of the universe, a phase where stars are still burning, galaxies are still connected, and information can still travel. This is not the default state. It is a very brief period compared to the full timeline of the universe. Before this, the universe was too hot for structure to exist. After this, the universe will be too diffuse for anything to happen. We are living in a rare moment where everything is still possible. Space still allows light to travel. Energy is still sufficient to sustain life, and complex structures still exist. This is not something guaranteed. It is the result of a temporary balance between gravity and expansion. When you look up at the night sky, you are not just seeing stars. You are seeing a special phase of the universe that, in the distant future, will no longer exist. Not because it is destroyed, but because it cannot be sustained forever. And that leads to one final thought. If the universe will end in complete silence, then the fact that we can observe, think, and understand it right now may be one of the rarest things that has ever existed. Not because we are special, but because the conditions that allow us to exist do not last long. And that is what makes this moment remarkable, not as a conclusion, but as an open question. After everything we have just gone through, a universe where stars gradually fade, where matter slowly decays, where no structure remains, it may seem like the story has ended, a space that is cold, dark, and almost completely still. But in modern physics, absolute stillness is not a concept that truly exists. Even when the universe reaches what we call heat death, it is not entirely nothing, because even the vacuum itself is not completely empty. In quantum theory, what we call empty space is actually a state with very low energy, but not zero. Physicists refer to this phenomenon as quantum fluctuations. In simple terms, even in the emptiest regions of space, particles can still appear and disappear. Not in an organized way, not following any easily observable pattern, but as extremely small fluctuations, brief and almost impossible to detect. That means, even in a dead universe, there are still tiny movements at the most fundamental level. Imagine a perfectly still lake, no wind, no current, but at a microscopic level, its surface still shifts slightly. Not enough to form waves, but not completely motionless either. The vacuum of the universe is similar. For most of time, these fluctuations do not create anything significant. But when we consider another factor, time, one important principle in physics is, if an event has a probability greater than zero, then given enough time, it will occur. And in the context of the universe, enough time does not mean millions of years, or even billions of years, but timescales that are almost impossible to imagine. Over such durations, extremely rare events begin to become possible. For example, a group of particles could, purely by chance, arrange themselves into a complex structure, not due to gravity, not due to evolution, but simply as a result of random fluctuations. The probability is extraordinarily small, so small that within any normal timescale, it would almost never happen. But if the universe exists long enough, that probability is no longer impossible. And this is where a controversial idea in cosmology appears. Scientists call it Boltzmann brain. This idea does not claim that it must happen, but it raises a question. If the universe exists for an infinite amount of time, what is more likely to occur? A fully structured universe like the one we observe today, or a random moment of awareness emerging from nothing? A Boltzmann brain, in theory, is a form of consciousness that appears temporarily from quantum fluctuations. No body, no real history. But it could exist for a brief moment, with a complete sense of memory and awareness, and then disappear. This idea may seem strange, but it follows the same principle. If a state has a probability greater than zero, then given enough time, it will occur. In a universe that lasts almost infinitely long, possibilities that seem impossible can become more common than we expect. However, this also leads to a major problem. If these random moments of awareness are easier to produce than an entire structured universe, then why are we existing in a universe that appears ordered like this? This is a question that modern physics does not yet have a clear answer to. It shows that even our best models are still incomplete. But there is one important point to emphasize. Phenomena like this, if they exist, occur at extremely distant timescales and probabilities. For most observable periods of time, the universe after heat death remains almost completely still. No stars, no galaxies, no new processes, only background fluctuations, very small and very rare. This brings us back to a simple observation. The universe does not truly end, but it moves toward a state where everything that happens becomes extremely rare. So rare that it becomes almost indistinguishable from nothing. In that state, it is not that motion does not exist, it is that no motion is large enough to create meaning. No structure, no interaction, no flow of energy, only small fluctuations disconnected from one another. And over time, the distance between particles continues to grow. Space continues to expand. Everything becomes more diffuse and more isolated. This means that even those rare fluctuations become less and less capable of producing anything significant. The universe does not stop. It continues to expand, making all possibilities increasingly remote. From this perspective, nothingness is not a clear endpoint. It is a process where everything gradually becomes less likely to occur. And if you go far enough along that timeline, the difference between something and nothing almost disappears. But the important thing is, all of this takes place in an extremely distant future, far beyond any timescale we can experience, far beyond the lifetime of stars, of galaxies, and of all familiar structures. At the present moment, the universe is still very different. It still contains light. It still has structure. It still has motion. And that difference is the most important thing. Because when we consider everything we have seen, a universe that began from energy, formed structure, then gradually dispersed, and moved toward near stillness, a question begins to emerge. If everything is moving toward dispersion, what does it mean to exist in a phase where structure still exists? And why are we here at exactly this moment? That is not a question physics can fully answer, but it is an observation that we exist in a period of time where the conditions for awareness and observation still remain. And when viewed across the entire timeline of the universe, that period does not last long. Not because it is destroyed, but because it cannot be sustained indefinitely. And that is the connection between a universe gradually becoming silent and the present moment, where everything is still unfolding. When we face the vast emptiness and the silent ending of the universe, we often feel the need to reconsider our place within it. But instead of focusing on size, try looking at the grand timeline of the universe. From a simpler perspective, our universe is about 13.8 billion years old. That number may seem long compared to a human lifetime, but on cosmic scales, it represents only a very early stage. The era of stars, the stelliferous era, is expected to last for another 100 trillion years. That means most of the universe's history will unfold after all stars have already faded. If we imagine the entire lifetime of the universe as a 24-hour day, human existence would occupy only the first few seconds, a very brief moment compared to everything that lies ahead. If we had emerged a few billion years earlier, when the universe was still young, heavy elements such as iron, oxygen, and calcium would not yet have formed in sufficient quantities. There would be no stable rocky planets, no complex chemistry, and perhaps no life as we know it. On the other hand, if we had emerged a few trillion years later, when dark energy has pushed galaxies beyond the cosmic event horizon, the night sky would look completely different. No distant galaxies, no light from large-scale structures. Only for a very brief period does the universe allow complex structures to exist. Observers in the far future will have no evidence of the universe's origin, no cosmic microwave background radiation, no traces of the Big Bang. From their perspective, the universe would appear as a small system, static and isolated. But at this moment, we stand in a very different position. We exist precisely within a rare moment in the timeline of the universe, a time when the universe is old enough to produce heavy elements, stars are still burning, and galaxies are still observable. We can see the past through observations from the James Webb Space Telescope, and we can project the future through physical models developed by Stephen Hawking and many other scientists. And it is within this short window that we exist. Perhaps The very expansion and separation we fear are what allow the universe to remain stable for a long enough period. A balance between the gravitational pull of matter and the expansion driven by dark energy. That balance does not last forever, but it exists long enough. What we observe in the night sky is not a permanent state. It reflects a special phase of the universe where structures are still connected. In the trillions of years to come, these conditions will no longer exist. Galaxies will gradually drift apart. Stars will fade one by one, and the ability to observe the universe will slowly disappear. But right now, everything is still here. Light is still traveling. Information can still be transmitted. Structures still exist. This is not the default state. It is a rare interval in the entire history of the universe. When you look up at the night sky, you are not just seeing stars. You are seeing a state that, in the distant future, will no longer exist. Not because it is destroyed, but because it cannot be sustained indefinitely. This does not need to be understood as a conclusion, but as an observation. A simple realization that we exist in a period of time where the physical conditions allow us to perceive the universe itself. And perhaps, recognizing that is the most important thing we can take from this entire journey. Not because it provides a final answer, but because it shows that, within a universe that is expanding and gradually becoming silent, we are still here to observe it. Closing. Our journey through the vast emptiness of the universe comes to a pause here. We have moved from the shimmering light of stars, which are only a small part of reality, through the invisible structures of dark matter, and into the continuous expansion driven by dark energy. The universe is empty, and according to our current understanding of physics, it will continue to become even more empty over time. But within that emptiness, there is something worth noticing. When the scale of reality becomes too vast to compare, the small concerns of everyday life seem to naturally feel lighter, not because they disappear, but because they no longer occupy all of our attention. What we observe in the universe does not carry emotional meaning, but the way we perceive it does. And sometimes, simply recognizing that everything exists within a much larger space is enough to create a moment of stillness. Not isolation, but distance. Not absence, but the natural state of the universe. Across billions of light years and trillions of years of time, to exist in a moment where we can still observe, think, and understand these things is not something common. And perhaps that alone is already worth noticing. Space Lull will always be here, accompanying you on your next journeys of observation. Thank you for taking the time to look beyond what we usually see each day.